Okay, this is Tuesday, and we are on week number 1, and this is day 1. Introduction to Programming Design. The more official name is Programming Logic with Language. We worked on tech background, we script example, and we started talking about problem solving. So let's get started on the tech background. A little review of what we talked about. First thing, we divided it up into these categories. We have the physical part of the computer. We have the software or the instructions that tell it what to do. And then we have this infrastructure that allows us to move information between different locations. We have people that use computers, and we have people that work on and design all of these things here. We're always striving from being a user to being more of an expert at one area or another, or many of them. In order to be able to do anything with technology, let me back that up. In order to be able to do anything with tech. Okay. Alright. We need to have some sound foundation of understanding how it works. Everybody should have that. By the way, it shouldn't just be programmers or network administrators or everybody should have that in order to be able to make decisions. So let's take a look. Our first key thing that we're going to look at here is data. Data is made up of bits, ones and zeros. We did an example down here. It could be coded as text, which we'll be calling strings in the programming world, or it could be coded as a number. We talked about float, which would be a number with a decimal point, or an integer, a number that's like a whole number, positives, negatives, and zeros. Okay? And these are represented differently in the computer. It's important to understand that. Here it uses a characteristic and a mantissa and so forth to represent a number. Here it uses some code. Doesn't have to be the ASCII code, but it is most of the time in a PC. We can look at this idea of 8 bits typically gives us a byte of information. I like to think of data as being raw facts. We take those raw facts and convert them into information, something that has value. We can take numbers and calculate some kind of budget that has value to us. We can manipulate the numbers and see the results for data analysis and get numbers that have values. What makes this conversion is software. Programs, list of instructions that are able to manipulate the data into some value of information. So let's talk a little bit about how that happens. What we're going to be working on in this class is design. We're going to design a solution to some type of problem. Our problem is going to be simplistic so we can better understand the design. A problem, a challenge, a way to make something better, make life easier, make life healthier, accomplish some task. Okay? So we'll just call it a problem, and then we think of designing some sort of solution, and the solution might best be done by computing. Make sense? Solution might be best done by computing for a variety of reasons. Okay? The task could be repetitive. Computer's good at that. The task could be dangerous. Maybe a computer's better at that. The task could be computationally complex. A computer is better at doing that. The task could be boring. Computers don't mind being bored. The task could be a huge quantity of information that needs to be processed. The computer doesn't mind how much you give it. Alright. So, we take some design, or at least we have some inkling of what we might want it to look like, and using technology we can develop source code. We're going to be writing in Python, but there are many other languages you could write in: C++, C#, C++, Go, there's just R, and there's lots of them. Java. Okay. So, these are usually referred to as high-level languages, and we write the source code, something humans can understand, and then we compile it into object code, something the computer understands. And that's a good enough definition at this point. Go from human readable code to machine readable code, the machine being a computer. And the term we use in order to do that work, we compile it. Okay? And we compile it to match an operating system. More on that in just a minute. Now, in the world of technology, we have libraries of information, code, that we can use. Let me give you an example. You don't have to write code that will sort. You can use something that somebody's already written and stored for in Python. So you can bring something in, okay, and that is called linking. We can link the object code to code that we already have and then create for us an executable that will execute on a particular operating system. So we have executables that would be applications or apps, and they communicate with a OS that ends up communicating with the hardware. So if we were to draw lines here how this happens, the app tells the OS what to do, the OS makes requests to the hardware, and the hardware responds. This layer in here is more than just the OS. There can be other things in there too, called system software. System software manages the hardware. So, we're going to look at an example. Inside a computer we have a processor, typically memory, and storage. Now if it's your phone, if you have a smartphone, the memory and storage typically is just combined in flash. You can think of it that way. But on most computers you have a hard drive, and then you have memory in the computer, and then you have this processor that does all the work. And they all communicate back and forth. So programs are stored in storage, and if you want to execute a program, you take it from storage and you put it in the memory. So programs that are being executed, the instructions in a program that are being executed, need to be in memory. Okay? Thinking of a typical PC or laptop and so forth. And then from memory, those instructions move. An instruction goes from memory to the processor, gets processed and sent back to memory. Okay? And that's how it works. Now, when we type a command on a scripting language, we're going to look at a scripting language here in a minute. We type the scripting language command, looking at a file here, it brings the file up, instead of compiling, it interprets the file. Okay, instead of compiling, it's an interpreter. Looks at all the lines, makes sure the syntax is okay, then it goes to the first line and starts executing it. We did an example of adding people to the Linux box today, or on Tuesday, I should say. So let's finish this up. Inside the processor, it basically is made up of arithmetic logic unit and the ability to move things around in registers and out of registers. And there's a variety of different registers, the accumulator and instruction register and so forth. What can it do? It can do arithmetic, add, multiply, divide, subtract, and all those other operations. And it can make logical decisions. It can have an if in terms of a logical decision. It can say, if this, and this would be, whoops, this would be comparing bits. If comparing the bits, are the ones and zeros equal, or is one group greater or less than the other? And if so, then perform some particular operation. In terms of flowcharts, okay, in terms of flowcharts, we can have an if-then statement. We can enter the box, then the box is either going to go the yes direction or the no direction, and then it's going to come back together. So it's an if-then. If it's true, perform these operations. If it's false, perform these operations. Come back together, and then continue the flow. And so we saw that in the script we looked at that added users. It was a bash script. Linux scripting language, bash. And allowed us to write a script, and in there was an if-then statement. If the user already existed, we checked for their directory. If they already had a user directory, then we skipped it. If that was yes, we just skipped adding the new user. If that was no, then here we added a user. And then this whole operation was inside a loop. Okay, so if I was to do this whole group was here inside the loop, so to speak. And so here, the loop, while this is true, we kept adding users. While it's true, we kept adding users. As soon as it's false, it end while. Then we went somewhere else in the code. Again, here, the computer is making a decision. Either this or this. Either the bits are the same, or one group of bits are smaller or less than the other, based on what you're comparing. Next thing, we talked about the internet, and we talked about the academic IT area. In here, we have some servers. They're in a DMZ, and this is the IP addresses of those. They're Linux, and work server 1, work server 2. And then we have the main part of campus over here. And we have this multi-layered switch that communicates between these two and here. And in reality, this is like a cloud at Nyack. That makes sense. We're really under one big cloud split into two parts. Now here, from the internet, this address matches with this public address, public IP. these are assigned to NIAC by our ISP, and they're also, these are servers in the academic area. These servers. Okay? So if you're outside of the academic area, like in the main area campus or the internet, you would use these addresses to communicate to the represented server. So, that takes care of Tuesday. Now we're on Thursday. This is week number 1, day 2. I'm going to put them all in one video. Intro to Programming Logic with Language. We did a course review. Talked about basics in the course. Access servers. We spent quite a while allowing the students to take some time to access servers and develop that. And we also talked about, when they had some extra time, doing their work on computer science. University of Waterloo, where the students can go in and work on Python. And I showed the students how I can see and access their work. Okay? We did a little bit of review on information communication technology basics. Did a little review. Didn't quite finish up, but we got close. Talk a little bit about the next step. Okay, so we talked about classrooms, MH216, PC 229. We talked about the switches in there. We talked about PCs communicated, and this route either from that room, either from this room through the switch, through the firewall, and out, or from this room. More or less, here is, let me back that up a little bit. The path here out, the path here out. So that stuff is right here. Okay, this is all in the academic IT. Talked a little bit about demilitarized zones, where those servers are. We reviewed the IP addresses. The students had to correct mine. I had that wrong. We mentioned a little bit, these are private inside numbers, and these are public outside numbers. And then we did the work on accessing the servers. And they should do this somewheres also off campus. And we still need to do this work, or at least go over how to do it from a Mac. So, wherever you're at, you should be able to, let's say you're at Cabin Coffee, you should be able to use some type of terminal software, and you should be able to come in and access the servers. We also talked, trying to understand a little bit of the internet and how Canvas is being hosted off campus. It's not hosted inside here. The servers that manage that are not inside the NIAC cloud. Just as an example. couple key things. The steps from source code to executable code. Understanding how operating systems are affected, more or less. We have iOS, Android, and then, you know, if I was to list a couple, yeah, probably should list Windows. Trying to be funny. Okay. When we create executables, they execute on a particular operating system. That makes sense? And that happens when we compile. If code's being executed in a computer, it is in memory. And in a lot of practical cases, the processor's only working on one instruction at a time, basically. Now we do have quad-core processors, so they can be working on different programs at a time, all these lines of instruction. But in basics, we get an instruction from memory to the processor, and the processor sends its results back to memory. And a program has to be loaded into memory before it can be executed, typically from some type of storage. Or, in the bigger picture, you're acting just as a client, and your software is being executed in the cloud. You're getting some service from the cloud. But in the cloud, that program is loaded into memory and it's communicating to the processor. Next week, we start talking about control structures. That's it.